Okay, so we have one more of our exercises from the handout to do, one more radioactive decay problem, and this is a good one. 200 kilograms of a radioactive element decays to 4 kilograms in 75 years. Find the half-life of the element. Now, let's organize our information here a little bit. I'm going to think about a table. T, f of t, where f of t is our usual a0 e to the kt function. So we start out with 200 kilograms. So at time 0, we have 200 kilograms. Our time units are going to be years here. And our function values are kilograms of whatever this element is. And we know it decays to 4 kilograms in 75 years. So when t is 75, we should have just 4 kilograms remaining. We want to find the half-life. Well, the half-life would be how long it takes for half of the original amount to decay, right? So if we take half of 200 kilograms is 100, it's really this value of t that we're trying to figure out here. We'd like to know at what time is only 100 kilograms remaining. So let me rearrange here a little bit. And so it's kind of like we want to plug in a y value and go back and solve for t, but we can only solve for t if we have our constants. So we know a0, right? a0 we are given in this problem. So f of t equals 200 kilograms, e to the kt. What we want is we want to find t when f of t is equal to 100 kilograms. But to do this, we first need to find k, the k constant in our function, this guy, right? Because it won't do us any good if we don't have a specific value of k. So to find k, we're going to use the fact that f of 75 is equal to 4 kilograms. In other words, we're going to use some of that given information. It's usually a point other than the initial value that helps us find the k value. So f of 75 is equal to 200 e to the k times 75. So I'm setting t equal to 75 here. And f of 75 is equal to 4. So 4 equals 200 e to the k times 75. And see, now we can solve for k. So 4 over 200 is equal to e to the 75k. 4 over 200 is 0.02. And if I take ln of that, that's ln of e to the 75k. ln and e cancel. I have 75k on the right. ln of 0.02 is 75k. So divide by 75. And I get my value of k of 0.02 ln divided by 75. Whoops, sorry, went down off the bottom. And it looks like I get negative 0.05. I'm just going to 0.052. Well, I guess 216. Better keep a few decimal places here. So 0.05216 is approximately my K value. And so now we're going to go back to the function. And put it together, right? F of t equals 200 e to the negative 0.05216 t. And now I can do the step that I was saying, really what we want to find out. We want to find t when f of t is equal to 100 kilograms. So this is to find the half-life. We're going to set the function amount to 100, half of the initial amount. So 100 equals 200 times e to the negative 0.05216 t, and solve for t. Okay. Well, once again, we go through our exponential function solving process. 100 over 200 is e to the negative 0.05216 t. That's a half, or 0.5, and so ln of 0.5 is ln of e to that exponential expression. And so ln of 0.5 is negative 0.05216 t. And let's see if I can fit it on this sheet of paper, since I'm so close to the end here. Can I squeeze it in? Ln of 0.5 over negative 0.05216 is my value at t, and I rounded that off at 13.3 years. 13.3 years. Is positive, right? Because I ended up taking a negative divided by a negative in my calculation. I'm going to try to zoom out a bit here to get more of this in the picture. Okay, we got just about everything there. Don't want to cover up the answer. So what we see is this value up here is 13.3 years. 13.3 years is the half-life of that radioactive element. Okay, now I want to say one more thing about graphing on the end of this, and no, actually I'm going to cut it off. I'm going to do that as a separate little video. So end of problem.